Hello, everybody, and welcome to our webcast. Together with our partner Xenix, today we'll present in-situ monitoring of laser processing operation with high-speed SWIR cameras. My name is Martin Labus from Laser 2000 Germany. I'm sales engineer for optical test and measurement, and how I like to call it, exotic machine vision. So that includes hyperspectral and especially IR cameras. From the Xenix side, Marc Larive will present the main part of this webcast, and in the end, we will have a question and answer session. Please feel free to put your questions whenever you feel like into the chat panel of the GoToWebinar dashboard. So at that point, yes, we will see the question and then you will get an answer anyway if it's presented in the Q&A or if we answer it directly. Laser 2000, founded in 1986, now provides more than 30 years of expertise in photonics and lasers. Laser 2000 Germany and its subsidiary in France, covering a big part of Europe, including the DACH region, Nordics, parts of Eastern Europe, as well as France, Spain, and Portugal. We also have partners in the UK and in the Benelux, so you can practically say Laser 2000 can provide you with solutions nearly everywhere in Europe. As you may not guess from the name Laser 2000, our portfolio doesn't only provide lasers, but everything around it, from laser and light sources via laser safety, of course, fiber optical networks, an upcoming topic for future communication, and of course, test and measurement, where my department is located. When talking about near IR and shortwave IR imaging, there are some introductory words from my side. So the NIR and SWIR spectrum start from approximately 780 nanometers and span around 2.5 microns. One of the most important points is that it's often considered as reflective IR, which enables pretty easy material classification by chemical composition or moisture content. But also a point that not everyone knows is that you can do also thermal imaging for processes where high temperatures, so above 550 or 600 kelvins, are involved. Also, the SWIR range is pretty advantageous for spot monitoring in laser material processing applications, as most of these lasers use wavelength around 1 or 2 micrometers. But more to this topic, my colleague from Xenix, Marc Larive, will give you now. Welcome, Marc.
Hello, welcome everybody. So my name, as Martin introduced me, is Marc Larive, and I'm working in Xenix as a strategic marketing manager. So today, thank you very much, Martin, for your introduction. So now I will focus on the use of the shortwave high-speed camera for the monitoring, in-situ monitoring of laser processing. So, in the first part, I would just introduce shortly Xenix company. Then we will dive into the world of laser in manufacturing and on the application that requires the high-speed shortwave camera, such as thickness or positioning monitoring, mile pool analysis, wavelength monitoring or wavefront sensing, all this kind of stuff. So first of all, some word about Xenix. Xenix is a leading edge infrared solution supplier, European one, and we are in the infrared for more than 20 years now, and we are leveraging on this strong background and all the knowledge of the technology that we got. And the goal is to provide really affordable innovation to our customers and to the market. So we are driven by the application and thus by the market. We listen the need and we answer to these needs. We are small, medium-sized company, so that we combine the flexibility of a small company and the support of a big company. And let's say the final goal and the ultimate goal for us is to turn all our technology and our expertise in real business value for our customers. So where to find us? As I said, we are a European company. We are based in Belgium, in Leuven, which is a suburb of Brussels. And we have some distributors, and particularly Laser 2000 in Europe. But we are all around the world. We also have a subsidiary, which is called Infrared in Singapore. We also have an office in the North America to serve the American market with people on the West Coast and the East Coast. So as you can see, we are all around the world. And try to switch to another. Yeah. Okay. So what do we cover? In fact, we cover all what is infrared, from the limit of the visible up to the long wave. And we design and manufacture and sell sensors, cores, and camera in the short wave between 0.7 to 2.5 micron, in the mid wave also with cooled camera, and also in the long wave between 7 micron and 14 micron with some uncooled camera. But now let's focus. Oh, I have some trouble, sorry for that. Yeah, let's focus on the shortwave offering and the shortwave topic. So in the shortwave, we have a vertically integrated offer. That means we manufacture the sensor, just the sensor, the core, that means sensor with its electronic, and also the full camera. We offer this in 1D with line scan sensors and camera, and 2D area scan. Okay, and for this we do everything. That means the heroic, we master the technology of the in-gas, and then we master the electronic and the camera and the software. So our core competencies, and this is very important, cover, especially in shortwave, all what is requested to offer the best camera. So I strongly insist on the detector technology, for sure, the in-gas technology, but also the readout design capability. And that means we design our own readout for the application we want to serve, and according to the demand of the market. Okay, we do not rely on any readout circuit that we will buy somewhere else, I don't know. We do it by ourselves. So we know it, and it has been optimized for the application. For sure, as I said, we master and design the electronic and the mechanic for the full camera. or what is the firmware, either the embedded software or the user software for the camera, but also some knowledge and deep knowledge in radiometry, because especially in long wave, our cameras can be used for radiometry, thermography, and very important, all image processing, image enhancement, because with our camera, customers want some time to make nice pictures. So camera and image enhancement is also a strong competence. So in the shortwave range, what is our offer? So as I said, sensor, cores, and camera, and we can propose sensors and cores or cameras in linear format from 512 to 2480 pixel. And by the way, we offer the fastest line scan camera available on the market worldwide, able to run at 256 kilohertz. This is Manx. And we also propose 2D cameras in the shortwave region, either QVGA, that means 320 to 56, or full VGA with the new one, which is called a Wildcat, able to run at 200 hertz, or even the very high speed camera, the Cheetah, which can be operated up to 1700 hertz full frame. That means in 645/12. So that means if you really need speed, and for the topic of today, you need speed, we have the kind of camera dedicated for that. So let's now talk a bit about the laser industrial application. Where do we need the laser and what is it for in manufacturing, in industrial manufacturing? So for the laser processing, let's say we have typically all what is additive manufacturing, okay, subtractive manufacturing, which is the opposite, all what is cutting, all what is welding, laser welding. And this is used, let's say, not whatever, but you can find it for different kind of materials. It can be for metal, for plastic, for semiconductors. Okay, in all this industry and for all this kind of application, you will find a laser processing. And for this processing, where do we need real-time monitoring? And why do we need real-time monitoring? So we'll see later that, let's say, main kind of need are for the positioning. I said thickness or measurement or positioning of the laser, power monitoring of the laser, characteristic of the laser, optimize focus to be sure that the efficiency of the process is the best and is most accurate. Okay. So let's first talk about what we can put in thickness measurement monitoring or positioning monitoring. So typically, why it is very important for some kind of additive manufacturing or for subtracting, such as cutting, which is in a way kind of subtraction. Yeah, here you have two pictures that I found on a manufacturer of positioning system, which demonstrate the importance to be sure of the real location of the process. If you don't monitor, then in additive manufacturing, for example, then you can add layer by layer, but you might have some, let's say, side effect or point effect, and you will not get something perfectly flat. If you monitor properly the addition and the position of where you are adding the material, then you can get something which is totally flat. It's the same when you want to cut. if you are cutting or welding at the bottom of something of a V shape like this, you want to be sure that if you cut that that level, not too low, not too high, to be sure that you monitor and you focus the laser at the best way. And if you have to cut this thickness and no more, you have to be sure that you stop at the right level. So one of the solutions to measure this positioning is what is called OCT, optical coherence tomography. So here is a schematic describing the technology. So you have the cutting laser here, coming here, and you have the measuring system all above, which is an interferometric system. So you have a light, which is with a large non-coherence, in fact, which is not really coherent light. Then you split it in two, one going to the sample and to the focal point and to the position you want to go, with focusing at the same position as the laser, and a reference beam, and then you recombine both and you look at the interference of it. That's very basic system, but very, very accurate. And here, with the measurement of the interference, you can deduce the exact position of the focus point. So this is another way of looking at it. You have the broad bandwidth source, you have the sample with either different location of reflection, either the position you are looking at, and a reference mirror, and then you recombine, and then you make a kind of spectroscopy. That's why it's called a spectral domain optical coherence tomography. And you, in fact, you process the spectra that you get, and it gives you the depths of the focal point here, or the reflection of this beam. Okay, so in order to do that and to use it in laser processing, you need something which is high speed, because this is a one-point measurement. So either if you want to measure a surface, then you need to scan. So you need to have a fast scanning system, and then a high-speed receptor, spectrometer. Or if you are using a high-speed laser and you want to be sure that it's always running smoothly, then again, you need to have a fast camera. You need a high-resolution camera at the spectrometer level, because in fact, the number of pixels that you get in your spectrometer then in your camera at the end is directly give you directly the resolution of the depth in the z-axis. So the more pixel you have, the more resolution you have. Okay. It has to be sensitive, because you only take a part of the beam, so you are in a low signal detection, in fact. And shortwave is also a good point, because you can optimize the wavelength depending on the environment and on the processed material, typically for semiconductor, because semiconductor is transparent in shortwave. So let's say silicon, excuse me, silicon semiconductor is transparent in shortwave, so you can typically see inside through it, and you can see the thickness and the depth of your cutting, for example. And you need also rectangular pixel because it's easier to align to make the spectrometric camera. And the bigger the pixel, the more signal you have. So in one direction, it is small to get good accuracy in depth, and the other direction, the bigger it is, the more signal you have. Okay. So typically at Xenix, The kind of camera we can offer for this application is the Manx. It's a very high-speed line scan camera, 256 kilohertz full line, and up to 2048 pixels, which gives you the best resolution you can get on the market. So it will give you a very high accuracy, or let's say very high resolution in the Z positioning, and a very high speed system. It also have a very nice, very good signal to noise ratio. It's in shortwave between 0.9 and 1.7 micron, and it is a rectangular pixel. So let's now go to another kind of processing, which is the additive manufacturing monitoring. So let's dive in the additive manufacturing. Two main way of doing that, either by laser powder bed fusion. It's a standard way of doing it. So here you put a layer of powder, and then you scan the laser on top of it, or on it, let's say, so that you can write, or you build a specific shape. By the laser, you focus on it and you scan it, and then you put another layer, and again you do that again with a laser, and again a third layer, and so on, and then you build the 3D item like this, and you can monitor in the real time with a shortwave camera, looking at what you are doing. Okay. Another way, excuse me, of doing it. There is one slide that I cannot see. Not a problem. The other way is to put the powder with the laser, okay, in the same time. So you don't have a laser, a powder bed, you just bring the powder in the same time as the laser. So it's just punctual. So what do you want to measure there? You want to measure the item itself. That means the piece that you are building, and how it builds. And in order to be sure that the building, the manufacturing is done in the right way, you look at the melt pool analysis. So the melt pool is in fact the small part of the powder which is melt by the laser and is sticking in a way to the rest of the already manufactured items. So it's just the very teeny point where you are building, where you are adding material. Okay, so it's important to make this analysis to be sure that the manufacturing is done properly. In order to do that, you need a camera to look at it. And because it's typically for metal, it's a high temperature, the shortwave is typically the right wavelength to look at it. It's, in fact, you are doing thermal imagery, but in shortwave, because the temperature of the melt pool is above 1000 degrees. It's very, very high, okay? So these are a real picture of what can be seen depending on the condition of the laser. And it's important to look at this to be sure that the parameters of your laser are properly set, so that the building, the manufacturing is done in the proper condition, and that at the end, the mechanical, in fact, the mechanical characteristic will be the good one. If you are too high power, then you could induce some defect in the same way you are building. If there is not enough power, the sticking of the different layer might be not so good, and so on. Okay. For this melt pool monitoring, which kind of cameras and what is the camera for? So I explain what is it for. So what are the characteristics of the camera? The resolution is important to get a good accuracy on the shape and the location in X and Y of the molten pool. Okay, So for this, you need as much pixel as you can. So you will need typically a 2D array, typically a VGA for a sensor, 64512. Speed is also very important because you are usually using high frequency laser and you are doing high speed scanning for the additive manufacturing. So in order to real time monitor this, then you need a high speed camera. So a typical example of what Xenix can offer for this is the Wildcat 640, which is a VGA 645 12 pixel, and it's running at 200 Hertz full frame. Very important, I didn't mention it, but very important, it's global shutter. That means you get a snapshot of each at each picture. It's not a rolling shutter where you can lose or you can have some drift or whatever. No, here you get all the pixels in the same time, so you get really a snapshot of the melt pool at a certain timing, and then you can build a real movie of the manufacturing process. Another camera is a Cheetah, which is a very high-speed camera, and then allows very accurate, high-speed, real-time monitoring of the manufacturing. So that was for the monitoring of the item or the sample that is being built, but you also can monitor the laser itself. So if you look at the laser for additive manufacturing, as Martin explained, usually are between 1 and 2 micron. So definitely shortwave camera are perfectly suited for the laser monitoring of this. Here we are looking at the ways of the laser. So we have to be sensitive at the laser wavelengths, okay? So shortwave is a good kind of camera to do that. And the high-speed camera is requested because of the high-speed process and the need for real-time monitoring. And the highest speed of the process, the higher the throughput you will get. So to get a nice monitoring, the higher the speed of the camera should be. So a typical example of the parameter you can monitor on the laser, this is a wavelength. So for this, in fact, you are doing the spectrometry of the laser to see whether there is a drift on the wavelengths of the laser, okay? And then you can, at least you know what happened, and perhaps you can react on it. It can be because of the environmental condition or whatever. So a typical camera for this is amongst 2480, that means a high resolution camera, so that you have a very high accuracy on the spectrometer, on the wavelength that you can measure. And it's a very high speed, 256 kilohertz, so that you can have a real-time monitoring of a high-speed laser. Another kind of analysis at the laser level of the laser parameters is the wavefront of the laser. That means the quality of the beam of the laser. Because the quality of the laser beam has a strong impact on the characteristic of the focus point. And the focus point at the end for additive manufacturing has a strong impact on the precision of what you are building, of what you are manufacturing, or of what you are cutting, okay? So the wavefront can be distorted because of the different optics that you have on the path of the beam, or also because of the air turbulence, because as I explained for additive manufacturing, the temperature is very high, so you might have high temperature around the sample, so you might have turbulence. So wavefront could be useful to be monitored. And once you measure the wavefront, you can correct it. So as I said, as I write here, in order to correct the wavefront, because of the distortion I mentioned, first you need to measure it. And what is the principle of a wavefront analysis? So it's very simple. Okay, you have the incoming light, a laser. You have the wavefront here of the laser, which are distorted because of plenty of reason. Okay, here you have a kind of adaptive optic that can modify the wavefront of the laser. Okay, then you take a small part of the beam. After that, you analyze it with a wavefront sensor, and either it is good and you do nothing, or in real time you can say, okay, the wavefront is not perfect and you should readapt the mirror here, the intermediate adaptive optic, to rebuild or correct, let's say, to correct the wavefront. And after that, on the main part of the beam, after this feedback correction, then you get as best as possible a nearly perfect wavefront, so that you can focus really on a perfect point. Okay, so that's the principle, and for sure it has to be done in real time to take care of the different aberration and different distortion that could occur. So for this, you need a high speed. So as a result, this is a picture I took. Okay, it's from astronomy, but the principle is exactly the same. To show you that what happened without the correction of the wavefront or with the correction of the wavefront. Here, this is a picture of something without the correction of the wavefront, and you cannot focus properly the light. And here, after correction, you can see that you can focus properly in just one single point, the beam. Okay, so at Xenix, what can we propose for wavefront sensing? First of all, as I explained, the main parameter is speed. So the speed is key for this application. Okay, so what we propose is it starts with a small camera, a Bobcat 320, which is a QVGA camera running at 400 Hertz full frame. But of course, you can speed up by windowing down the camera. It's already a good starting point. Then you can go to a bigger camera, with more resolution, the Wildcat, which is 645/12, and then you have the 200 Hertz full VGA speed. Of course, if you go to a smaller resolution, you will definitely increase strongly the speed, and then get something which is more real time, which enable a better real time correction. And by the way, the Wildcat also has a better noise level, lower noise level, which is important because, as I said, you just, to measure the distortion, you just take a small part of the beam. So it's important to have something which is very sensitive. And then if you really want something running at high speed, then you can use a Cheetah running up to 1700 Hertz on the full VGA frame. And of course, if you window down this camera, you can reach several kilohertz for sure. And there you have a real-time capability of correction. So as a conclusion, as I said, the laser processing is more and more common in the industry, and is also more and more demanding on the monitoring and on high-speed camera because of the evolution of the process. Second point, what we can say is that for additive laser manufacturing, lasers are used usually in shortwave. So the shortwave camera are typically the good one for this kind of monitoring. And with the recent cameras now that you can find, and especially at Xenix, you can really run at high speed, up to 250 kilohertz on a line scan, on a big line scan, or 1700 Hertz on a 64512 2D array. So these real high-speed cameras in shortwave open new possibility of monitoring for this kind of processing. Thank you very much, Martin. And I'm open to discussion and to questions.
Yes, Mark, thank you for these really interesting insights. Yes, I think the audience will bring some questions up. So let's see for a first shot. Yes. So how is it about Windows? The question is, does one need windowless cameras for the process presented?
Okay, so it will depend, in fact, mainly depend on the process. Typically, when you are trying to analyze the shape of the laser, you are trying to analyze a laser, the less optics you put in addition in front of the laser, the better it is. So to avoid an interference, yes, for laser shaping, monitoring, windowless is usually is better. This could apply to other kind of laser analysis. The less, let's say, the less optics or optical element you put in addition to what you really want to do, the better it is. So that could be, but let's say mainly it's used for laser shaping analysis, beam shape analysis. It could be also for Wavefront. It could be interesting for Wavefront something, for example.
Okay, thank you. I think yes, that was a good point. Let me just genau. So let's see. Yes, are all the cameras presented of global shutter or type, or are there also rolling shutter cameras?
All the camera I presented from Xenix are a global shutter. Definitely.
All global shutter. Yeah.
And they are global shutter, and for this kind of monitoring, it's usually the best solution.
Yes, I see so too, because yeah, rolling shutter, especially when moving or when you have high-speed processors, they tend to produce some artifacts in the imaging. Yeah, so
yeah, if you're looking for speed or fast events, it's better to get a global shutter. Otherwise, you will have some effect of the speed on the rolling shutter when you combine both.
Yeah. Okay. So yes, talking about the SWIR cameras in the laser process monitoring, can SWIR cameras be used also for cooldown monitoring of the material after laser processing? So maybe just let me start. In my introduction, I already said that especially shortwave infrared will work, I think, from 300 degrees centigrade on. So there you typically can see an emission. But for further investigation of the cooldown process, I think you will need longer wavelength cameras. So Mark, please go ahead.
Yeah. Typically, for the very high temperature, you can look at the temperature cooling down, moving down with a short wave. But once you cross, as you said, several hundreds of degrees C, let's say up to 400 or 300, whatever, this kind of order of magnitude, usually it's better to use a long wave camera, such as Xenix. We propose the SWIR, which is a real thermographic camera in order to get the accurate temperature. In shortwave camera here, you will see a high temperature thermal effect. You will not measure the precise and accurate temperature. If you want to get really the accurate temperature of the item when it cools down, then use typically a SWIR long wave and cooled camera.
Okay, thank you. Yes, I think that's also another follow-up question. So if maybe you can tell if there's, or do you have the possibility to calibrate SWIR cameras for thermographic measurements, or is this only for long wave or mid wave IR?
Yeah. Usually it's for long wave IR that you use thermographic. For short wave, it's much more complicated, and yeah, it's difficult to get accurate measurement, really thermographic accurate measurement, because you have a lot of things that has to be taken into account. Typically the lens and okay, plenty of things. So usually with shortwave, you do thermal imaging. You do thermal imaging, okay, not thermographic. In standard, we do not propose the thermographic shortwave camera, but for thermographic measurement, yes, you move to the long wave that can reach high, even 400 or 500 degrees C. You can measure it really with an uncool and with a CRST. 400. I think the standard is 400 degrees C for the CRST.
Okay, okay, thank you. So another question. That's something that, yeah, that's a question. Do you have any experience in implementation of IR camera for laser soldering processes, low temperature and low signal level?
Okay, you mean short wave camera or long wave camera? Because depending on the temperature of what you are looking at, if you just want to measure, let's say something with temperature, you choose the wavelength of your camera thanks to that. So laser soldering is not really low temperature at the focal point. Depends on what you are looking at, but it could be higher temperature. It depends. Really, it depends for that.
Yeah, I guess at this point, one can say so. Like in the question before, when you're looking at the, when you see how far up your product is heated, or the soldering is heated, then you can work in the SWIR. But when you maybe follow the cool down process and precisely measure, you should go down to with a calibrated thermography camera. Yeah, and therefore there are industrial suited solutions like Mark mentioned, the CRST with onboard thermography capability and so on.
But for high temperature, let's say measurement of the soldering, yes, you can monitor it with a shortwave, as far as I know.
Yep. Okay, so let's see if there aren't any more questions at the moment. Please feel free to contact me directly, even after the webcast, or when you see this, the record of this video on YouTube or wherever. Please feel free to contact us at Laser 2000, and in case we are not able to answer your specific questions, we are glad to forward it directly to Mark and his colleagues and his experts at Xenix, and you will get an answer no matter what. That's what I can say. Sometimes maybe the answer is, I have no clue. But in general, we reply to your questions. So please note, our webcast series will have a short summer break within the month of August. But after that, on September 15th, our next free webcast, which is held in German together with our partner OptoSigma, we'll give a practical approach how to equip a laser laboratory, starting from the optical table up to the optics and optomechanics use. So thank you for your attention, and we're looking forward to welcoming you again after our summer break.
Thank you.
Thank you.
Bye-bye.
Bye.